You can't find it. What we're doing is looking at problems that can be modeled like a linear programming problem, which is something that you're well familiar with, except we want to require either all or some of the decision variables to only take on integer values. Okay? That changes the nature of the problem because instead of looking at some sort of a polytope or a polygon in the geometry, so something that is continuous and you've got infinitely many solutions, you change to something where there's a discrete set of solutions and it's one of a finite set typically that you have to find the best of. Okay? And so the simplex method doesn't work anymore because the simplex method finds something that's fractional. Now just rounding, we saw yesterday that just rounding the solutions of the fractional solution to the nearest integer doesn't work. It can be very far off the actual optimal solution. And we looked at two problems, and I can only find one of them in my papers, but you remember what they were. So the first one was which items to put on a ship to transport to maximize income, and the other one was this kind of matching problem where you're trying to find the best match between a set of girls and a set of boys, or whatever these things can be. It's a very universal model, so that you maximize the total utility or the total satisfaction expressed in some numbers. Okay? And you can formulate it as an integer program. We saw that yesterday. So your decision variables, there's going to be one decision variable that can only be a 0 or a 1. So these are integer numbers. One for each possible couple. And then, sorry. Yeah, and then the objective function is just the sum of those. So wherever the couple is created, this variable will be 1, and its utility will count as positive. And when it's not created, this variable will be 0, and it won't count as any. 0. And then the constraints that we had in this case were that Alice has to marry exactly one of the boys. So all the possibilities for marry added together have to be exactly 1. Okay. And that we insist on all these variables being as 0 or 1, that will mean that exactly one of them will be 1 and all the rest are going to be 0. And that's the same for everybody else. Okay? So these are the constraints. And in the other case, we had a similar formulation, and we never said how we actually find an optimal solution. So that's what we're going to do now. Right. And it's something that there is not much more that we can do other than go through all the possible solutions, but we can try and go through all the possible solutions in a smart way. So perhaps we can save ourselves some work. And this sort of, or this class of algorithms, or this algorithm that we're going to look at is called a branch and where is it? Oh, no. A branch and bound algorithm. And as its name would suggest, it's based on two ideas. One of them is the idea of branching into different sub-problems of the problem that we have to solve. And the other one is the idea of bounding, which saves us some work. Okay, so let's first explore the branching idea. Okay, so when we're trying to solve, I'm going to draw a tree. Usually, you capture the whole solutions in a kind of a tree-like structure. So at the top, we have the problem that we're trying to solve, and that is the problem of finding the best match between the boys and the girls. So that problem, okay? And at the beginning, we don't have any constraints, but so this is our problem. I'll call it S, and we don't know what its optimal solution is, and we just have all the constraints of the problem in here. Now, because each of these variables can be either 0 or 1, we can split all the feasible solutions to this problem to those that where the first variable, say, is 0, and the ones where the first variable is 1. And that's exactly what the branching is going to do here. So we'll be looking at solving a problem. Okay, I'll call it S0, where XAP is going to be set to 0. Right? And the second problem we want to solve is, I'll call it S1, and this is where XAP is 1. Now, one of these subproblems is going to contain the optimal solution, because there is no other option for XAP. It can either be 0 or it can be 1. So if we can solve a problem in which XAP is always 0 and find the optimal solution for that problem, and we can also find a problem where XAP is equal to 1, then by looking at which of them is the better one, we can find a solution to the original problem. That's the whole idea of branching. Now, what we can see is that, look at the constraints here. There are some constraints in which XAP appears. Okay, so if XAP is set to 1, then that and that both have to be 0, because otherwise you wouldn't, if you make one of them 1, you'd already have 2, and then there's no way of getting a sum of 1. And if XAP is 1 here, then both XBP and XCP have to be 0 as well. So if we set XAP to 1, that already determines the value of some of the other decision variables, those 4. Okay, so in the second case, we already know that in this case, well, we have that XBP has to be 0, and also XCP has to be 0, and XAR has to be 0, and XAS has to be 0. In this case, we can't make any other conclusions, because if it's 0, it could still be either one of the other ones, so this one. What we can look at, okay. Now, basic idea. Now, how do you go on? Well, you just continue and keep and branch both of these subproblems until you find a feasible solution where all the values of the variables have been determined. Okay, so how do you choose which variable to branch on? Doesn't really matter, usually. So I picked XAR, so we have 2 options. Again, for XAR, it's either 0 or it's 1. I'll just label this S00. Now, if we have XAP and XAR is equal to 0 because of this constraint, if that is 0 and that is 0, that has to be 1. Okay, so in this case, we know that XAS is equal to 1. And because XAS is 1, that means that was S. Sean is getting Alice, so Sean can't marry anybody else. So here you get X. BS is not and S. There you'd have something else, and I don't want to go through all of this. So there are some other things that you know. Whereas here, for example, I could do xbr equals 0 or xbr equals 1. And there's plenty of things that are determined already. So we know XAB, XAR, XAS, XBP, XCB, XBR. Then when you look at all these other constraints, you realize that we also have to have these values. Okay, and so now, now all 9 of these decision variables are already determined by the constraints and the choices that we have. Okay, so if we fix XAP equals 1, that forces these values of 0 to all those 4 variables. And if we then decide that XBR is 0, well, XBP is 0, XBR is 0. One of the XP somethings has to be a 1, so it needs to be XBS is 1. And yeah. And XAS is 0, XPS is 1. XCS has to be 0 because exactly one of the something S's has to be 1, and that's already the D1. And what else? XCR has to be 1 because XC something has to be 1. And XCP is a 0, and XCS is a 0, so it has to be XCR, which is 1. Okay? So now, like this, we already know all the values of the decision variables. So when we look at the objective, we can calculate the objective in this case. So I'm not sure which ones they are. I've changed this from 0.6 to 0.7 to get it better. I apologize for that. That's the wrong value last week. So I say this is 0.7. I'm not going to do it now by hand, but what I'm supposed to get is that the objective with these values of the decision variables is supposed to be 1.8. Is that what you're getting? Anything unclear? Right, so is everything clear so far? Yeah, you've made some choices. Some of the decision variable values have been forced, and once I know all the values, I can work out what the value of the objective is going to be. Yeah? And similarly, here on the other side, everything is forced as well.
Why is that 1.8?
Why is that 1.8? It is because, is it not? So which ones of the variables are 1? It's AP, and it's BS and CR. So AP is this one, and BS that's this one, and CR that's this one. Oh, so it's supposed to be 1.9? I think you're right then. I don't know. What have I messed up? So maybe I haven't changed it from 0.6 to 0.7. Who knows? At some point, I changed one of the values because I was getting better results with the different values, and now I'm not entirely sure which way I changed it. So okay, so if we stick to 0.7, this is supposed to be 1.9. I'll double check after the lecture to make sure that I've got all the values correct. Okay, so in the second case, we're supposed to get what? XBS now has to be 0 and XCR has to be 0 and XCS has to be 1. So in this case, what do we have? XCS, so that's this one, and BR, that's this one, and AP. So that's also 1.9. Maybe I wanted to keep it 0.6. Because that's consistent with, okay, let's try to, apologies, let's try to keep it 0.6 and then this is, and then this is 1.9. Okay, is everything clear up to this point? Yeah? Good. So in these two problems, we already know what the optimal solution is. So we also know what the optimal solution of S1 is. And because we want to take the better of the two children. So the better one is the one on the right. In this case, the optimal solution is also going to be 1.9. Which we've determined down there. Okay. Well, here on the left, none of them has been fully determined, so we still don't know what the values are. So we'd have to branch here and branch there again. And if we did it, then tentatively it will look like this. If probably check that I'm getting the right values of the objective. So on the left, we get AS and BR and CP, and that really gives me 2.3. And the second one, AS and BP, 1.3. And CR, that's 2.2. So that looks correctly on. This gives me 1.9, by now 0.6. And it's probably 1. So once we've got these solutions, we can see that, well, here it doesn't matter. They're equally good. So the optimal solution is still going to be 1.9. That's a problem. And this is a problem. The better one is 2.3. So this the optimal solution here is going to be 2.3. So the optimal solution here is also going to be 2.3. Use that one. And if we go back, then the best that the children again is that one, which is 2.3. And so like this, we can determine that the best possible solution. So the optimal solution is so that's the idea of doing the branching. Any questions about this at all? But what I said was that there was a second idea, which was the bound idea, which allows us to save some work sometimes. It's not guaranteed. So that's the example. This one. So the idea is that if we have this problem, call it S, that's the one that we're solving. Then we can write a similar problem, which is to maximize, which is the same problem, more or less. And I'll call it down. Can you spot the difference?
One says integers and one just says zero.
Yeah. This one doesn't want those numbers to be integers necessarily. So this is a standard linear programming problem which you can solve using the simplex method. Now, if you do solve, oops, using too much of the paper. So when you solve this using the simplex method, the optimal solution is going to be x1 is 20/7 and x2 is 3. x2 is 3. And z is 59/7. So can we get any sort of information about the original integer problem from this? Any idea?
X2 is a very nice one, so probably keep X2 as 3.
Probably not. That's the tricky bit about it. You really don't know anything about what x1 and x2 are going to be in the optimal solution. They could be anything still. But there's something about the objective in the optimal solution that we know that it definitely cannot be better than this. Because if you found numbers that satisfy that, and the objective is more than 59/7, then those values of x1 and x2 would also satisfy these constraints, right? So it couldn't be that the optimal solution of this is 59/7. So there's no way you can find x1 and x2 for this problem that will give you a better objective value than this one. Making sense? Okay, so never you can find anything better. So now we know, and we don't know much, but we know that the objective is no more than 59/7, and in fact we know that the objective is going to be an integer, so it can't be more than 8 in the optimal solution of the original problem. Okay. So now we would like to do a similar branching thing as we did before. But before it was easy because it was either 0 or 1, and here it's not so easy. So here we're trying to solve S. And what we found is, now the relaxed problem, so the R gave us Z equal to 59/7, and x1 was 20/7, and x2 was 3. Now, if you had x1 and x2, if they had to be 0 or 1, then it's kind of easy to you just pick one of them and you set it to 0 on the one hand and to 1 on the other. But here you can't do that. So the way this is normally done is you look at something that has a fractional value, so in this case x1. Now you know that x1 seems to be that the best value is somewhere between 2 and 3. 0.07 is close. So what you do here is you look at all the possibilities where x1 is no more than 2, and on the other side you have, not x2, sorry, x1 is at least 3. And like now you've captured all the possible solutions because x1 can't be anything between 2 and 3. It has to be an integer number. So if it's more than 2, then it's at least 3. Okay? So can't be anything else. So now what happens is you try to solve this problem. I'll call it S2. I'll call it S2. And in this problem, so S2 has all the constraints of S, and also it wants x1 to be greater than or equal to 3. Now it turns out that if you try to solve this linear program with the additional constraint that x1 is greater than or equal to 3, you find out that there is no feasible solution. So you have no feasible solution, even ignoring the integer constraints in this case. Okay, so that's good. So now we know that x1 can't be more than 3. X1 has to be less than or equal to 2. So what we do is we call this S1. So if we do the R, oh, I didn't say why I call it R, and you add that constraint, turns out that in this case, the optimal solution is going to be Z is going to be 15 over 2, and x1 is going to be 2, and x2 is going to be 1/2. So we still don't know the optimal solution, but we know it's certainly not going to be better than 7. Even if we don't insist on x1 and x2 being integers, there's no way of making it, well, yeah, it's constrained, there's no way of making it better than 7. So better than 7 at the end. But again, so there's nothing we can do about this other than branch again. And so the way this is branched is just like I said before. A variable with a fractional value, if you have several of them, then you can pick any of them. And somewhere between 0 and 1. So you can look at one possibility, which is that x2 is going to be 0, and the other one is that x2 is 1 or more. And again, S1, S1, 2, and this. So now when you solve the linear program using the simplex method, say, with all those constraints that we've always had, and these two additional constraints, so if I keep that one and I add that one as well, what's going to happen is that the optimal solution is going to be x1 equals 2 and x2 equals 1, and z is equal to 7. So now we don't have to branch again, because we've already found a solution that is all integer. So in that particular situation, in this case, we know what the optimal solution is. These two are. That's good. Now, if we solve this problem, what we're going to get is that x1 is 3 over 2. Well, x2 has to be 0. It's one of our constraints. And that gives us, because it's 4x1 minus x2, the objective is so we get the objective is now 6. Do you want to branch again? Why not?
it's only going to get revised. Is that value?
Because?
Is that value is only going to decrease if you go further?
Exactly right. I was going to say because there's no paper left, but then no matter what we would do here, we would always only get an objective that is no better than 6. Adding constraints. Adding constraints, that means that the optimal solution is getting worse and worse. There's no point trying to find the best solution there because we know it's never going to do better. This is the principal way how it saves us some work. So we can stop branching here. Because no solution in that branch can be better than the optimal solution of S12. Okay. Which means that going backwards, so this is the best one we found. So here the optimum is also going to be 7, and here it's going to be 7. And now we'll find the optimal solution. So this is how it works. Summarize, you start by removing the integer constraint, solving the linear programming problem. That gives you a solution which is not necessarily integer. If it is integer, then you're very happy because you've already found an optimal solution and there's nothing else to do. But if it isn't, you pick one of the variables with a fractional value, whichever. There's no good rule that would always work very well. And you create 2 subproblems. One of the subproblems, you make the variable smaller than its optimal value. On the other side, you make it larger, and so and like this you continue. And when you stop branching, you stop branching in 3 different situations. One of them is when the problem becomes infeasible. So there's no feasible solution in satisfying all these constraints, so there's no branching. The second case when you stop branching is when the LP solution is all integer, because then you already found the solution. And the third situation when you stop branching is when the value you get is worse than the value of an integer solution you've already found. So it depends on which order you do the folding in sometimes. Because if you hadn't found this before going on with that, so you have to branch that and keep going. But if you have found it already, then there's no point branch. But if it wasn't integer and had 7, then you still don't know what the optimal solution is. If it's integer and the value is better than somewhere there, then there's no point. I'm not stop. Any questions? Right, the homework question is a bit challenging, but you have a week to do it. And then one of the assignments that's coming is going to be to solve the problem in this manner. That's it.